So something I didn't stress very much is that, okay, we got a thermal state up here for the observer at infinity. Well, first of all, the basic idea was that what you observe at B, which is near future infinity, far away, comes from what there was at A, just outside the horizon. And what you observe at B was thermal, so it was conspicuously far from being a pure state. At A, that happened because you only made measurements outside the horizon. And we know that if you take a pure state but restrict yourself to measurements on one side, it becomes equivalent to a mixed state. That's something we discussed when we were discussing Rindler space a couple months ago. The difference is that the observer near the horizon could step across and measure the state on the other side, whereas the observer at infinity has no access to what's behind the horizon. So at A, if you interpret the state at A as a thermal state, you're doing so because voluntarily you don't want to step across the horizon. But as an outside observer at infinity, you're stuck interpreting it as a thermal state. You can't see farther. Gosh, it is time to start. Okay. So one thing I didn't get time to say last time is that this thermodynamics is actually unstable in flat space, in asymptotically flat space. We had thermodynamics, but it was actually unstable. That was because the temperature was 1 over 8 pi g times the mass, or 1 over 8 pi g times the energy. So the heat capacity, dE dt, was negative, which corresponds to an unstable system. We discovered that there was detailed balance such that a black hole could be in equilibrium with radiation at the Hawking temperature. But suppose you have this equilibrium and you disturb it slightly with, let's say, a downward fluctuation in the mass of the black hole. If you slightly reduce the energy of the black hole, it becomes hotter because dE dt was negative from this formula. If it becomes hotter, it will radiate more, and therefore its mass will go down even more. So if we had the opposite sign of dE dt, then if there was a downward fluctuation in the black hole, it would have become colder, would have absorbed energy from the radiation, and returned to equilibrium. So positive dE dt would correspond to a stable equilibrium, but negative dE dt is an unstable equilibrium. So black hole thermodynamics in asymptotically flat spacetime doesn't completely make sense because thermal equilibrium doesn't, the statement that a black hole radiates at the Hawking temperature is correct. But the idea of thermal equilibrium between a black hole and radiation doesn't completely make sense because the ensemble is unstable. Now, if we turn on a negative cosmological constant so that we're in asymptotically anti-de Sitter space, then black hole thermodynamics is better defined. And in particular, this doesn't happen. In asymptotically anti-de Sitter space, if you have a sufficiently massive black hole, it can be in stable equilibrium with radiation. Unfortunately, we're running out of time for this course to explain that. So we're not going to do that case, and we're only going to be discussing asymptotically flat black holes. But I thought it was worth mentioning, since we will, both on this point and some things we'll say later today, we're going to be saying some things that aren't completely well-defined in an asymptotically flat spacetime. So I think it's worth mentioning that everything we'll say has a completely well-defined cousin with negative cosmological constant. So what I want to explain first today is the Euclidean approach to black hole thermodynamics. By Gibbons and Hawking. not too long after Hawking's great discovery. So we might start as follows. Bekenstein, motivated by the area theorem. Remember, the area theorem says that the black hole horizon area can only increase. And Bekenstein knew that entropy is supposed to only increase, so he suggested that the entropy might be a multiple of the area. And this turned out to be correct. But from that point of view, you could ask, why not S being a multiple of the area squared, or S being any function of the area whose derivative is positive? If all you know is that the entropy is an increasing function, instead of being the area itself, it could be any increasing function of the area. However, let's put in factors more carefully. If we restore, well, I won't restore the speed of light, but if I do restore Planck's constant, then the Bekenstein formula has precisely one factor of h bar in the denominator. I think I wrote it once when we were talking about the Bekenstein bounds, just by way of saying that that factor is the reason that black hole entropy is so big in ordinary terms. So the entropy of a black hole the mass of the sun is 10 to the 20 times the entropy of the actual sun. And that's related to h bar in the denominator. But anyway, something you'll notice about a single factor of h bar in the denominator is that it's like an action. Or maybe I should say, like the, well, so the Feynman path integral is an integral over fields with the weight, which is the exponential of minus something that I'll call the action, where I is proportional to one factor of 1 over h bar. So precisely because Bekenstein took the entropy to be the area rather than some other function of the area, the dependence of the entropy on h bar is precisely like that of a classical action. And Gibbons and Hawking interpreted black hole entropy in terms of a classical action. So for this, they look at the black hole in Euclidean signature. So I'm going to write all these formulas in 4 dimensions, though they have analogs in any dimension. So first, here's the Schwarzschild metric in Lorentz signature. Now to go to Euclidean signature, we just replace t by I tau. And then we get a Euclidean signature metric Well, in Lorentz signature, we had a singularity, which was at r equals 0, but the horizon at r equals 2 gm was smooth. What happens in Euclidean signature? So in particular, in Euclidean signature, does it remain true that the horizon at r equals 2 gm is smooth? Well, to answer that question, you can introduce a convenient new coordinate so particular capital R is 0 at little r equals 2 gm. And then in terms of this coordinate, the metric becomes r squared times d of tau over 4gm squared plus r over 2gm to the fourth dr squared plus r squared d omega squared. So here, little r is understood as a function of big R that you would get by inverting that relation. So this is a way of writing the Euclidean version of the Schwarzschild solution. Now, near r equals 2gm, we can drop this factor, and we can replace this by a constant. So near r equals 2gm, we just get r squared d of tau over 4gm squared plus dr squared plus 2gm squared d omega squared. That's near r equals 2gm. Well, this factor is certainly completely non-singular. It's just the metric of a sphere times a constant. It's the metric of a sphere of radius 2gm. But what about this part? Well, compared to polar coordinates, on R2, where we could describe R2, for example, by r squared d phi squared plus dr squared, where phi is an angular variable with period 2 pi. So as we all know, this is a representation of a completely smooth metric on the plane, where the apparent singularity at r equals 0, where the metric seems to become degenerate, has to do with the fact that the coordinate system is bad at r equals 0, capital R equals 0. So likewise, all that's happening here at capital R equals 0, which is little r equals 2gm, is that the coordinate system is becoming bad, provided we give tau the correct periodicity. And so tau over 4gm should have a period 2 pi. So tau should have a period 8 pi gm. Now, tau is imaginary time. All the tau was we took Schwarzschild time t and defined it to be I times tau. So tau is literally imaginary time of a Schwarzschild observer of an observer at infinity in Schwarzschild coordinates. In the original Schwarzschild description. So we've discovered that the Euclidean metric, well, I think I'll say it better. We've discovered that the Schwarzschild solution is periodic in imaginary time. With the period beta h, which was 8 pi gm. And that period corresponds to the Hawking temperature. Something I might have emphasized more last lecture than I did is that the Hawking temperature up to a constant of order 1 is 1 over the size of the black hole. So the Hawking temperature corresponds to photons whose Compton wavelength is comparable to the size of the black hole. So that means that the black hole is strongly emitting photons at a wavelength of its own size or bigger, and only weakly emitting photons smaller than its own size. That was why in his original paper, Bekenstein had trouble making sense of the interaction of the black hole with photons whose wavelength was the size of the black hole or bigger. That's precisely when the Hawking radiation is significant. Okay, so let's now discuss what this metric is once we give tau the correct periodicity so that the metric is completely smooth. So near infinity, at far away from the black hole, we just have R3 times S1, where the S1 has circumference beta h equals 1 over th. We might have slightly obscured that by the change of variables, but let's just go back to the original description. The original description near r equals infinity, we can just ignore these factors of 2gm over r. And then this much is just the metric on R3. And this factor is just the metric on Euclidean time, which now parameterizes a circle because we declared that tau is a periodic variable. So at infinity, we just have R3 times a circle. And the circle has an appropriate circumference corresponding to the Hawking temperature. Now, when you go into the interior, the circle becomes smaller, and it shrinks to a point at the horizon, at little r equals 2gm, because the circumference of the circle is just the square root of this factor times 2 pi. Sorry, not times 2 pi. The circumference is 8 pi gm times the square root of that factor. Tau is periodic with period 8 pi gm, but the length element is not d tau squared, but d tau squared times this. So the circumference is a function of little r, which is constant near infinity, but goes to 0 at the horizon. So at the north pole in the sphere, well, for example, I want to draw a picture, but I can't really draw a picture of a 4-dimensional geometry. So I'm going to draw a picture of a 2-dimensional slice by restricting to one point on the sphere, and then just drawing the 2-dimensional geometry parameterized by r and tau. It looks like a semi-infinite cigar. Well, it's a cylinder of revolution. I haven't drawn that perfectly, of course. So that's a 2-dimensional slice. A more 3-dimensional picture would be that. So there's literally a hole in space. So I'm trying to imagine a 3-dimensional picture where I suppress the 4th dimension parameterized by tau. So everywhere there's a circle that has a variable radius given by this formula. So the radius at infinity of the circle I'm not drawing is 2 pi gm, but it shrinks to a point in the interior. But just drawing the 3 dimensions parameterized by r and the polar angles, whose metric I usually summarize in the d omega squared, The three-dimensional picture is a copy of R3, but there's literally a hole in space. The hole in space is where the missing circle contracts to a point, making a smooth four-dimensional geometry without boundary. So the interpretation of this by Gibbons and Hawking was that you do the path integral, you study a thermal ensemble at the Hawking temperature. Well, how would you, okay. In field theory, first of all, how would you study a thermal ensemble? To study a thermal ensemble in field theory without gravity, we would study a thermal ensemble by a path integral on R3 times S1, where the S1 would have circumference beta. Now, in field theory without gravity, we just declare by fiat what the geometry is in which we do the path integral. But with gravity, of course, we can't specify the geometry by fiat. We can only specify what it is asymptotically. So with gravity, instead, we have to say that we do a path integral on spacetimes asymptotic to R3 times S1 beta. So we can't say what the metric is in the interior. That's up to the dynamics of gravity to decide. We integrate over all possibilities. But we can specify asymptotic boundary conditions. And by saying it's asymptotic to R3 times S1 beta, we incorporate the fact that space is R3 and the temperature is 1 over beta. If we instead wanted to do gravity in asymptotically flat spacetime, we would do a path integral on metrics asymptotic to R4. But at non-zero temperature, we do a path integral on metrics asymptotic to R3 times S1 beta. Now, in this path integral, the black hole is an instanton solution. It's a non-trivial extremum of the path integral. Now, this can't be pushed too far in the context of asymptotically flat spacetime. I told you just at the beginning of the lecture that the black hole thermodynamics in asymptotically flat space is unstable because the specific heat is negative. And similarly, this instanton is unstable. And more fundamentally, the whole thermal ensemble is unstable even before you get to include gravity. The black holes. Because at a thermal ensemble, you at least would expect a constant energy density. But a constant energy density in infinite space doesn't make sense with gravity because it would all be inside it. It would all be collapsed to a gigantic black hole, right? If you have an energy density rho, energy density per unit volume rho in volume V would have a total energy of order rho V and a size R is V to the 1/3. So GE over R is much bigger than 1. And just when GE over R is equal to 1, you would get a black hole. So the thermal ensemble in which the black hole is a soliton doesn't really make sense in asymptotically flat spacetime. It does make perfect sense in asymptotically anti-de Sitter spacetime. So in asymptotically anti-de Sitter spacetime, not only does the black hole make sense as a soliton contribution, but it turns out that its action is negative if the mass of the black hole is sufficiently big, and it dominates the thermal ensemble. So the Gibbons-Hawking discussion as was essentially discovered by Hawking and Page in the following decade, the Gibbons and Hawking discussion makes more sense in anti-de Sitter space. And that's very important in contemporary work. But since we're running out of time for the course, as I said, we won't get to discuss that. What we are going to do is to discuss how, well, what else Gibbons and Hawking said using the Euclidean picture. So, the path integral around the black hole instanton solution would contribute, well, the partition function in the black hole sector would be the exponential of minus the action, and then minus the classical action of the solution. Then you could make a series in small corrections due to loops. These are small if the mass of the black hole is big. Well, I should say, if m is much bigger than the Planck mass. And then you could worry about some collective coordinates. So you might say that you get a factor of space-time volume from the position of the black hole. So indeed, you might argue that if you want to take into account black hole entropy, you should compute black hole entropy. You should include an entropy due to the possible position of the black hole. Usually we don't, and we assume the position is known, and we don't get an entropy from there. I'm just going to explain what Gibbons and Hawking said about the classical solution. Since we have a thermodynamic system, they interpreted Z the way you would for any thermodynamic system. It's, well, the number of states times the exponential of the contribution of one state. The contribution of one state at inverse temperature beta is e to the minus beta e. And the number of states is the exponential of the entropy. So they interpreted the exponential of minus the action of the classical solution as the exponential of S minus beta e. Of course, Z is, the free energy is usually defined so that Z is e to the minus beta F. So in their path integral setup, Z was e to the minus I. So they interpreted the classical action as beta times the free energy of the black hole. So it turns out that it's a little bit tricky to calculate the action of the classical black hole. We'll discuss in a little bit how to do that. But assuming we knew how to do that, we would know S minus beta E, and then we might want to know how to calculate S. And there's a standard thermodynamic formula, which is that S is minus 1 minus beta d. I'll write it in terms of the action. So we're interpreting the action as S minus beta E. So let me just explain why we would expect this formula to be true. I think I don't need a minus sign here, though. So one term is just S. And then we get minus 1 minus beta d beta acting on beta times E. That's 0. And then we get minus beta times ds d beta minus beta times dE d beta. But that's 0 since dE equals T ds. So, well, this formula, except written in terms of the free energy, so, sorry. Well, in the thermodynamics book, it would be written in terms of the free energy rather than the action. But anyway, this formula is one that you probably met when you studied thermodynamics, or you might have at least. So, to find the entropy, what we're going to do is to calculate the classical action and then just act with 1 minus beta d by d beta. I am troubled, though, because I do have a minus sign in my notes. Sorry. What did you say? Yeah, that's right. Yeah, sorry. I is minus S minus beta E. So we need a minus sign here so that it goes away here. Okay. It's better to straighten that out at the beginning rather than the end. Okay, so we want to apply this formula, but we need to know what's the action of the black hole. So what is I for the Euclidean black hole? Well, naively, at least the first formula for the action in general relativity you'd run into in textbooks with the usual Einstein-Hilbert action, which actually in Euclidean signature needs a minus sign, which I initially forgot when I was trying to prepare this lecture. So it would have a plus sign in Lorentz signature, but a minus sign in Euclidean signature. But it turns out that the action actually needs a surface term. You have to add what's called the Gibbons-Hawking-York surface term. The reason you do is that the scalar curvature R that appears in the metric, in the action, has second derivatives of the metric in it. Whereas ideally, classical actions only have first derivatives. So let me review why it's good if classical actions only have first derivatives, and then we'll understand what's bad about having a second derivative here and why we should add something. So in mechanics, we'd have a typical action with first derivatives. For example, like this. And then we look for a wave function that's a function of x. And a corresponding path integral we do. Let's say we specify a time interval delta t. Well, okay. We specify initial time t1, final time t2. And we integrate over all paths that go from x1 to x2 in time t2 minus t1. And that gives you a transition amplitude from an initial state, psi in of x1 to psi out of x2. By integrating over all paths that start at x1 and end at x2. Now, to make sure this is physically sensible, we should go on and continue up to x3 at some later time. So maybe I better call this psi1, psi2, and then psi3 of x3. And we'd like to know that what we get by integrating over all paths from x1 to x3 is the same as we get by integrating over the first interval, also integrating over the second interval, and then integrating over x2. Well, to show that the amplitudes multiply, we need I of x3, x1 on the big interval is the sum of the smaller actions. And then, because the action is a sum, the integrand of the Feynman path integral is a product. And if you do the path integral on this segment and the path integral on this segment, and also integrate over x2, you've built up the big path integral over the larger segments. And that's a basic fact about how quantum mechanics works. Now, at the endpoints, we specified x, and therefore we can't also specify the canonical momentum, x dot. And therefore, we can't assume that x dot is continuous at the transition point x2. And consequently, it's a very good fact that there's no x double dot in the action. Had there been an x double dot in the action, then because x dot can't be assumed continuous, there would be a delta function at the boundary point. And the big action would not be a sum of the two little actions. It would be the sum of the two little actions plus a boundary contribution. Now, the reason that there's no x double dot in the action, so we could have written the action as minus x times x double dot over 2. But if we had, we would have integrated by parts to get rid of the second derivative. And reduced to the standard situation where we don't need a boundary term in the action. If for some reason we decided not to integrate by parts to get rid of the x double dot, we would need the boundary term. The version of the action that works is the one without the second derivative. If you want to use a version of the action with a second derivative, you need to compensate by adding a boundary term that would have canceled if you'd integrated by parts. So that's the situation in ordinary mechanics. Now let's go back to general relativity. In general relativity, the scalar curvature does have the second derivative of the metric in it. And we can't get rid of it by integrating by parts, because there's just no covariant way to integrate by parts in this formula. That formula is perfect the way it is, and it's not equivalent to anything else that we could get by integrating by parts. So we're stuck with the second derivative in the action. And therefore, we're in a similar situation to what would have happened in mechanics if for some reason we decided to use a version of the action with a second derivative. We have to compensate by adding a boundary term. And the boundary term was constructed by Gibbons, Hawking, and York. So M, I assume, has boundary. M is a space-time with boundary of M. The boundary term is the integral over the boundary of M, G3x, where H is the metric on the boundary. And I'll explain, we'll get back to K in a moment, but K is the trace of the second fundamental form, trace of the extrinsic curvature. I'll explain better what K is in a bit. So in Lorentz signature, the formula is still true, except you'd want a plus sign for both terms. Now, this is, okay. I skipped a step where I intended to explain why we'd get disaster without the boundary term. Now, remember, what we want to do is to calculate the action of the black hole solution. But naively, the action is 0. Since the black hole has R mu nu equals 0, and therefore it has R equals 0. So if you used the Einstein-Hilbert action as well, described in many textbooks at least, you would decide that the black hole action is 0. It's crucial to take into account the Gibbons-Hawking-York boundary term because everything actually comes from there. So, well, I'm going to explain what K is. So, first of all, I'll define extrinsic curvature. So, we have hypersurface. And let n be the unit normal. I'll first give the general definition, and then I'll put it in a more convenient form. So the hypersurface might be in a flat space, for example. So it might be completely flat, but the hypersurface could be curved, although it's embedded in a flat space. If that's the situation, then its unit normals curve around. And if you parallel transport the unit normal using the connection of the ambient space, that parallel transport will be non-zero, even if the ambient space was flat. So if n mu is the unit normal, then we take d mu n nu, where d mu is the ambient connection, but restricted, so mu is tangent to the hypersurface. In other words, we only calculate covariant, well, we only can calculate covariant derivatives along h because the unit normal is only defined along h. So we calculate those covariant derivatives we can of the unit normal, and that's called the second fundamental form. Oh, sorry. It has two standard names. One is second fundamental form, and the other, which I think is more common nowadays, is extrinsic curvature. What extrinsic means here is the opposite of intrinsic. So the hypersurface is a Riemannian manifold in its own right. As such, it has a Riemannian curvature. To compute it, we would take the induced metric of the hypersurface. That's just the metric h is just the metric g of the spacetime restricted to the hypersurface. Then we would calculate the Riemann tensor of h using standard formulas. That would give what's called the intrinsic curvature of the hypersurface. This thing is called the extrinsic curvature of the hypersurface. And it has to do not with the hypersurface itself, but with the way it's embedded in an ambient space. To give an example, suppose we're in 2 dimensions in a flat space. Then the hypersurface is just a one-dimensional curve. And intrinsically, a one-dimensional curve is flat as a Riemannian manifold. There's no curvature in one dimension. But this extrinsic curvature is non-zero. Now, as a shortcut to help us understand the extrinsic curvature better, let's remember the coordinate system we used when we were discussing Hawking's theorem about the Big Bang. We used the coordinate system associated with the orthogonal geodesics to the hypersurface. So we put the metric near the hypersurface in the form well, the x's, let's say, are coordinates along the hypersurface. And I'll define h by t equals 0. So t will be a normal coordinate. And then given that, we wrote the metric along the hypersurface as hij of x and t dxi dxj plus dt squared. And that was very handy in in eventually getting to Hawking, well, in understanding Ray-Chodori's equation for time like geodesics, and also therefore getting to Hawking's theorem about the Big Bang. Now, in this coordinate system, Kij is very easy to calculate, and it's just 1/2 hij dot. And in particular, we see that it's symmetric in I and j. In a general coordinate system, of course, k will still be symmetric, but it will be given by a longer formula. And for in the action, what we need is the trace of k. So that is 1/2 of hij dot. And you might recognize that that's something we ran into previously in the course. That's d by dt of the logarithm of the square root of the determinant of h. So in a coordinate system with this property, a coordinate system of that form, that's a convenient formula for k. So where V is the volume density of the hypersurface, the square root of the determinant of h. So now we're going to try to implement that to make sense of this formula for the action of the black hole. So what we're going to do is cut off the black hole at a very big radius and evaluate the action. But we'd better do the same thing for empty space without the black hole. So if we just take empty space at beta equal the Hawking temperature, so then the metric is just and tau has period beta Hawking. Well, we cut it off at a very large radius, r equals curly r, let's say, where the metric is just the metric of the hypersurface. So we cut it off on a large hypersurface where r is curly r, and the metric of the hypersurface is then d tau squared plus curly r squared d omega squared. And we can use the preceding formulas because the metric, see, with R playing the role of T. We have an R-dependent metric of the hypersurface plus dr squared. So we have the metric in the form that we assumed here. So, well, H is d tau squared plus r squared d omega squared. So the square root of the determinant of H is r squared. So K, which is d by dt of the log of the square root of the determinant of H, is 2 over r. So the action of empty space cut off at r equals curly r is what? Well, it's the integral over the hypersurface where r is curly r, d tau d omega, square root of determinant of H, times K, because K is 2 over R. And the square root of determinant H was R squared. So this integral is, well, the integral of the unit sphere gives us 4 pi. Tau integrates to beta H. And then we have 2R. And I guess we shouldn't forget that there was a minus 1 over 8 pi g in front of this. So, sorry. We're supposed to set r equal to curly r. So finally, that's what we get for the action of empty space cut off on a big sphere.
Sorry, just a question. So,
Yes.
apart from the fact that we get a trivial answer if we don't have a boundary,
Yes.
is there any other intuition for why we need to cut our space?
Well, as we're going to see, the boundary term, okay, this is a nonsensical looking boundary term because it's proportional to the cutoff. There's certainly not any physics in it as far as I know. What's going to happen when we do the black hole is that we're going to get the same ridiculous thing. So when we compare them, we'll subtract and cancel it. And then there will be a finite correction, which will actually give the black hole entropy. So I feel the best answer is that in anti-de Sitter space, see, as I've told you, black hole thermodynamics in asymptotically flat space is not completely well defined. And there definitely are steps that could be criticized. I would say more or less all of them. Sorry. The Hawking radiation itself, a black hole radiating empty space, is clear. But when you try really seriously applying thermodynamics to the situation, all steps can be criticized. So I feel that the best derivation, I'm tempted to open the floor for comments from the audience in case someone has another answer to suggest. I will in a second. But the best answer I can give is that this, in anti-de Sitter space, it would have been clear. Then you don't add a cutoff. The universe actually goes off to infinity. But the correct formula for the action does involve a boundary contribution. And you get this kind of answer. But let me invite comments from the audience on this one, because some of you have worked in the subject and might have other answers in mind. Why is this the correct procedure? Going once, going twice? Okay. If there aren't any suggestions for answers, then I'm going to stick with my answer, which is that the honest place to do all this is anti-de Sitter space, and then it's clear one can more precisely justify this.
So, but do you just need a space-time that has a boundary intrinsically to as well, right?
Well, in anti-de Sitter space, well, you're out there near infinity making measurements. What's inside could be either empty space or the black hole. And they have different actions from your point of view. That's the best answer I can give in the context of an asymptotically flat spacetime. In the context of anti-de Sitter space, everything is well defined and you get this kind of answer. Because for other purposes unrelated to the black hole you discover, but intuitively for the reason I said, anti-de Sitter space behaves like in many ways like a big space with a big box. Even though the box is at infinity, you do need the boundary term in the action to get sensible answers for all kinds of things. And it gives the kind of answer I'm just in the process of deriving for the black hole. Any other questions?
But like, the action is also divergent in ADS, or you also need to...
Well, definitely. So
Okay, good.
the action is divergent. It's more divergent than this. This was only a linear divergent. In ADS, it's more seriously divergent. That's interpreted in terms of a renormalization of the cosmological constant in the boundary theory.
Yeah, okay.
So the action is divergent, but it has a natural interpretation in the boundary theory. So the infrared, the regularizations you need in the infrared from the bulk point of view match the UV divergences in the boundary theory. That's the general story in ADS CFT. But, okay. I'd say that the physical ideas are similar to this, except that you could argue it's more clearly correct in anti-de Sitter space. I mean, I would argue that. But, okay. But what I'm telling you is pretty much what Hawking and Gibbons said. Hawking and Gibbons pretty much justified it the way I have, I think. And they didn't know it was better defined in anti-de Sitter space because that was not discovered till about 8 years later by Hawking and Hawking and Page. Okay, now we have to do the same calculation for the black hole. So now we do the same thing, but the metric is 1 minus 2gm over r d tau squared. And then there's this dr squared over 1 minus 2gm over r plus r squared d omega squared. And now we cut it off at, again, r equals curly r. And we repeat the calculation. Now we have a different, okay. We repeat the calculation with a slightly different metric. And we get a different answer for the boundary term. So see, before we got an answer that was linear in R, before we got an answer that was linear in R, but now there's a correction of order gm over R in the metric. So now we're going to get a correction of order gm over r compared to what we had in the flat space case. And if you work out the coefficient, it comes out to be like I've written. Which, of course, you can write in different ways. It's also minus beta r over g plus 4 pi gm squared. Or minus beta r over g plus beta squared over 16 pi g. So then the action of the black hole cut off at r minus the action of empty space cut off at r just involves this correction term. So that's what Gibbons and Hawking interpreted as the entropy, the action of the black hole. So then they defined the entropy by a formula we discussed before. And that's just beta squared over 16 pi g. Which indeed for Schwarzschild black hole comes out to be A over 4g. So that comes from the usual formulas. Beta h is 8 pi gm, and area is 4 pi times 2 gm squared. Formulas that we've used numerous times. Yes?
So I have a question. So here we are cutting off the black hole at some large radius r.
Yes.
The length of the Euclidean circle is actually smaller,
Yes.
slightly smaller than
Yes.
beta h.
Yes.
And actually, I would think we should compare the action
Yes.
of the empty space with the
Yes. 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 That's correct. We should. I might comment on that on Thursday, but I don't want to try to do it now. But your statement is correct. I didn't do the calculation that gave this factor. Well, any other comments or questions? Yes?
I have a question about something about 20 minutes ago when you introduced the thermal gravitational particles.
Yes.
So in ordinary non-gravitational thermal field theory,
Yes.
we can actually derive the fact that thermal correlators are given by a path integral on a cylinder,
Yes.
essentially by slicing the cylinder and then seeing that that corresponds to taking a trace.
Yes.
Is there a similar interpretation of the gravitational particles?
Well, you've asked a very fundamental question, which has to do with the biggest mystery, perhaps in physics, almost. And the answer is no. There's not a clear explanation. Your question does get at one of, well, something I was going to say in about 5 minutes, but I'll say it now because of the question. So, I left out a couple of steps in the derivation, and Yiming has pointed that out. But basically, this derivation gives a sensible answer for the entropy, but it gives no insight about what are the physical states which are contributing that entropy. And the reason is that the circle shrinks to a point inside. So usually, So if we have no gravity, we have the path integral on R3 times a circle. And as you've said, we can then deduce that a path integral in a circle is a quantum mechanical way to compute a trace. But it's important to have the circle. Now, in the Euclidean black hole, there is a circle at infinity, but none inside. And since there's no circle inside, there's no way to interpret the path integral as a trace. Hence, there's no understanding of what are the states that contribute to the entropy. So the Gibbons-Hawking calculation gave a sensible answer for the entropy, but no insight about what are the physical states that are contributing that entropy. So your question touches at the basic reason that black hole thermodynamics is mysterious.
If we didn't have a separate way to compute the entropy, would we just not take this calculation seriously?
Well,
Or is it the fact that it agrees with the other calculations that makes it mysterious?
well, this calculation does a lot more things right than I've been able to tell you, and we're running out of time to explain everything. You might want to look at Wald's book, where he discusses some classical aspects of black hole thermodynamics that we won't have time to get to. And there are a few more things I will explain Thursday. So there's a mountain of things that work correctly. So it's got to be correct. But the fundamentals are totally unclear precisely because of your question. The fact that the circle shrinks to, maybe, I'm not totally sure it was obvious to everybody. If you want to get a trace, that means you need an initial value surface in which you formulate states. And then the states propagate around a circle to give a trace. So it's fine if you have a circle, but it's not fine if you don't have a circle. And precisely at the horizon, we don't have a circle. It shrank to a point. And so well, that's the root reason that black hole thermodynamics is mysterious, as I've said. Any more questions or comments? Well, let's take another look at the Euclidean black hole. So remember, the Euclidean black hole, well, let's just look at the two-dimensional slice. So, okay. So there wasn't any circle in the interior, and that prevented us from interpreting the thermal ensemble in terms of a sum over states in space. But there is something which we can do, which is that we can find an interesting initial value surface. So we have a symmetry, tau going to minus tau, with fixed points at tau equals 0 and tau equals beta h over 2. Remember that tau is a periodic variable. So let me draw the fixed points out of the symmetry. So on the circle at infinity, here's 0, here's, well, this is meant to be 0, and this is meant to be beta h over 2. And then they go in. But at the origin, they become indistinguishable. Remember, tau is like the angle in polar coordinates, and at the origin, it becomes undefined. So these two lines that go in meet at the origin in this picture, which corresponds to the black hole horizon. So we have an initial, well, in this two-dimensional picture, we have a geodesic, actually, which comes in from infinity, goes around the tip of the cigar, and goes back. It's a geodesic, and it's also the fixed point set of a symmetry. Now, when we multiply this times S2, we make a 3-manifold of topology R times S2. R is this geodesic, and S2 is the S2 I'm not drawing, parameterized by the polar angles. Now, this is a fixed point set of the symmetry tau goes to minus tau, and that means if you continue from tau to real time, it remains a real hypersurface. So this hypersurface can be drawn in Lorentz signature. In Lorentz signature, we've got this picture that is best understood using the Kruskal-Sakaris coordinates that I briefly introduced in one lecture, although I was hoping most of you knew about them. And tau goes to minus tau in Euclidean becomes t to minus t in Lorentz signature. And there is indeed a hypersurface that's invariant under t goes to minus t, and that's this. So the hypersurface in this picture at time 0, which goes straight through the horizon from the left asymptotic region to the right asymptotic region, corresponds in the Euclidean picture to what we get if we take this geodesic that went in from the infinity to the tip of the cigar and back. Now, first let's then discuss the physical interpretation. So first of all, in the Lorentzian picture, we have two asymptotically flat regions. And this is a smooth complete hypersurface that goes from one to the other. It's a perfectly good initial value surface in general relativity, except it's exotic because it's two-sided. It describes a space with a wormhole in it that connects two different universes. Two different universes that can't communicate with each other because of the topological censorship that we learned about a few months ago. So, in this picture, that corresponds, let's say, to the right universe, and going out to infinity corresponds to the left one. If I was to draw a picture of this three-manifold as a three-manifold, well, I can draw a two-dimensional slice of it. It looks something like this. At infinity, we have R3, but it's connected by a wormhole to a second R3. This is the right side, and this is the left side in this Lorentz picture. And it's the, well, front and back, but I've labeled them as right and left in this Euclidean picture. Now, there's a natural quantum state. On the hypersurface H. which is prepared by Euclidean path integral. In general, how do we use the Euclidean path integral to prepare an initial value state on some manifold? The general strategy, if we want to prepare an initial value state on hypersurface H, is we take a Euclidean manifold that has H for a boundary, and then the path integral in that manifold will produce some kind of quantum state on the boundary. If you want to get the vacuum state, you take M to come in, you come in from tau equals minus infinity. And then propagation over infinite Euclidean time will prepare the vacuum state. But a path integral in any Euclidean manifold will prepare some kind of state. So to prepare a natural quantum state on this hypersurface H, we need a 4 manifold whose boundary is H. And the Euclidean black hole has given us one. The path integral on the bottom half, or the top half, it wouldn't matter because of symmetry, produces a quantum state on the hypersurface H. It's called the Hartle-Hawking state. I think it was also sort of described by Israel, so some people call it the Hartle-Hawking Israel state. Well, what is the Hartle-Hawking state? So, first of all, near infinity, I'll call it psi HH. Near infinity, psi HH is the thermofield double on R3. Because near infinity, remember, near infinity, the Euclidean black hole is just R3 times a circle. We take half of the circle, the bottom half, so we have R3 times an interval. The interval has length beta h over 2. And as we've discussed in the past, a path integral on a manifold times an interval produces a thermofield double state on that manifold, well, on 2 copies of the manifold. So near infinity, we have a thermofield double state on 2 copies of R3. But they're linked in the interior. So to an observer on either the right or the left side, the Hartle-Hawking state looks like a thermofield double state. A thermofield double state in the presence of the black hole. And again, there's a more precise version of that picture in anti-de Sitter space.
So does the temperature go to like infinity as you're near the horizon?
Well,
Is that the limit?
you see, well, many people would say that the temperature diverges near the horizon, but if you're a stickler, you'd say the following. Temperature is only well defined if it's constant on a distance more than 1 over the temperature. And that condition is not satisfied, so therefore the statement that is often made is not precise. I try to avoid it, but I'm in the minority. Any other questions or comments? Yes?
You could still have the same signal for a one-sided black hole, right? So in that case, what would the...
Well, we started with we tried to study a one-sided black hole. And we got the cigar by analytically continuing a one-sided black hole. But then we were not able to make a quantum state of a one-sided black hole from it. The reason is that we need to make a hypersurface. So we try to make a hypersurface in this picture. We come in from infinity, we have no way for it to end. So we can't make a one-sided hypersurface. The only way to make a hypersurface is to keep going and come back. And then we make a two-sided hypersurface. So to get a pure state, we get eventually a pure state of a two-sided system. I repeat though, we started with a one-sided system. We analytically continued it. We got a new insight about why the black hole has a thermal interpretation. But it did not give us any way to make a pure state of a one-sided system, because there was no appropriate hypersurface. We can make a pure state of a two-sided system. That, of course, is what usually happens in thermodynamics. As we kind of discussed at one point, there's no Hilbert space that contains the typical state of a thermal system in infinite volume, but there's a two-sided version of that, the thermofield double Hilbert space. So the fact that we could make a two-sided Hilbert space, well, I made a particular state, but because we have a hypersurface, we can make a whole Hilbert space obtained by acting on that state with arbitrary operators. So the thermofield double state that we constructed is contained in a thermofield double Hilbert space that contains all the excitations around that state. And that exists for the two-sided system, but we did not discover anything that would enable us to construct a one-sided Hilbert space. That's related to the question you asked a while ago, whether our computation could be interpreted as a trace. It could not be. And related to that, we did not discover a one-sided Hilbert space. We only have a two-sided Hilbert space. It's clear in this Lorentz signature picture. How would you make a one-sided Hilbert space? You want an initial value surface on which to define the states. But there's no one-sided version of that. You start at infinity trying to construct your hypersurface, but the space keeps going, and all you can do is go out the other end. So that's another aspect of why black hole thermodynamics is problematical. Any more questions?
Basically, we don't have interior black hole.
You could call this region up here the interior. But the black hole, in this picture, the black hole is kind of a hole in space, right? It's a hole in space that connects you to another universe. I think we should call it a day, and I'll see you Thursday for the last lecture, and I will try to finish up. Well, I've had to renormalize my expectations of what the course will consist of, because we're running out of time. I aim to explain two things on Thursday. One is the Susskind-Uglum observation that generalized entropy is better defined than either term is separately. I'll try to explain that. And then I'm going to try to explain the proof of the generalized second law. And I hope to manage to finish that on Thursday. There's a slight problem because Yiming's question, I realized, is something I should have explained better. So ideally, I also would find 5 minutes to discuss that. But we might have a unitarity problem on Thursday. We'll see. Okay.